for having me here at this very intriguing meeting. I guess I owe you a personal introduction. Most people here probably won't know me. I'm a condensed matter physicist by training. And be alert, there will be some language issues in this talk. I hope we can fix them. How did I end up here? Well, it all started with the physics of the Syk model, which I'm sure most of you are aware has become hugely popular in condensed matter physics. And at some point I started talking to Julian, somewhat later to Pranjal, inching closer towards holography in the process. And in all these discussions, matrix theories were center stage. So they were all, in a manner of speaking, revolving around matrix theories. And I mean, so far so unsurprising. I mean, matrix theories are immensely important both in quant math and in holography, string theory, gravity, etc. Looking back to a history of many decades. But you know what really struck me, and both from a scientific but also from a social perspective, is how totally different the perspective of matrix theory is in quant math and chaos on the one hand, and gravity and holography, string theory on the other hand. Now you might say, I mean, who cares? I mean, different fields, different interests. But the thing is that when it comes to holography, and most certainly the holographic readings of the Syk model, we crucially need both. We need these two perspectives. The more stringy gravitational one, which I understand always emphasizes topology, but also the one of quantum chaos, which tends to focus more on correlations, spectral correlations, but which in fact represents a geometric viewpoint. So we have kind of a dichotomy between geometry and topology. And that's, and now I'm showing a slide, that's in a way motivating this talk. I want to kind of review the two different readings of matrix theory, focusing, of course, on the chaotic side. I mean, I couldn't possibly tell you something about your own field, but hopefully in a language which you find accessible. And if not, please interrupt me anytime during the seminar. What I'm telling you is kind of owed to collaborations with various people from which I learned a lot, but specific references are to the papers shown down here, which I wrote with Julian and Pranjal. The outline of all this is that I start with a review of matrix theories in quantum chaos. Apologies to those who know this stuff, but I just have to set the stage here. And then I will try to discuss what I mean by this tension between topology and geometry. And we can then ask together if there's anything useful to be learned from that. Okay, so here it is, our protagonist matrices, high-dimensional matrices. And what I mean by matrix theories is pretty canonical, I guess. We are talking about partition sums realized as integrals over realizations of these matrices, which for the time being are Hermitian, but we don't need much more on structure information. And then we have an action which is realized as typically as some trace invariant polynomial of H. Yeah? This will be my working definition of matrix theories. I will be more specific later on. And let me now very briefly, just to set the stage, wrap up what I mean by gravity, particle physics, string theory view of this. There are many applications which I don't have to tell you about, but let me just pick out one. I mean, the discretization of surfaces, two-dimensional surfaces, where we do the following. We can consider a very simple prototypical one-matrix model realized as a cubic matrix model shown here. I think you all know these actions. And we can approach it in the limit of large n perturbatively in a 1/n expansion, which can be organized in the Toph double line notation, where we have in 1/n propagator and cubic vertex is indicated here. And when we now start doing our perturbation theory, we realize that the 1/n expansion is in fact a topological expansion. So we can organize this into a planar, if you will, diagrams And at next order, we have toroidal ones, and then we progress in the number of genera in a 1/n series. Now, I also learned that there is a way of making this more quantitative, powerful approach going by the name of topological recursion, which in my understanding is essentially the following. We look at a correlation function, usually a trace of a resolvent, and correlation functions built by taking the matrix functional average of a bunch of these. And we can organize this in a topological series, organized according to 1/n, which is 1/a genus expansion. And it then turns out that contributions of a given topological order are hierarchically realizable as sums over contributions of lesser order. And this is a quite powerful way of organizing the sum. I understand it's an exact approach. We could also call this a solution of the model. But what I want to emphasize is that from my application perspective, this approach is also formal, in the sense that it will not give you in the end just a function of your energy arguments, but we rather get a more structural representation of the correlation function we are interested in. Okay, and that's for the time being it. I mean, the kind of more topology-oriented view of matrix theories. And let me now compare this to the one which, I mean, the chaos view, yeah? Or if you want, quant-mat. And here we focus on correlations, on spectral correlations. What do we mean by that? It all starts with a mantra, which is known as the Bohigas-Giannoni-Schmidt conjecture 1980, which states that quantum systems which are chaotic in their classical limit are equivalently described by random matrix theory or matrix theory at large timescales or equivalently at low energy scales. And if you are not so familiar with this, let me illustrate this on one of zillions of possible examples. This here would be the example of a nuclear reaction, heavy nuclei, classically chaotic systems. And what you see here is very old data, scattering resonances, which are in one-to-one correspondence to the energy levels of the corresponding systems. And how do we connect this now to Bohigas-Giannoni-Schmidt? It starts with the identification of two energy scales. One is implicitly defined as the energy scale below which we expect the random matrix correspondence to hold. And this one is often called Thouless energy in the parlance of the field. And this Thouless energy is now assumed to be much larger than the second energy scale, which we can identify, namely the average spacing between levels. And the statement is now that the statistics of the position of these levels is equivalently described by matrix theory. How do we make this concrete? We describe the statistics in terms of correlation functions, very often two-point correlation functions of the spectral densities. Rho is the spectral density of this data. And we look at correlations at a certain energy difference omega. And this omega, this energy difference at which we are probing the function, is then set in relation to the average level spacing to define a parameter S. And keep an eye on this S. This will be our the fundamental parameter in this talk. I mean, not much more what we need. And these correlation functions now expressed can be expressed in terms of the resolvents, which we mentioned earlier already. And you can compute this now numerically or analytically or whatever and compare to what? To random matrix theory. And what I mean now by random matrix theory is a matrix theory defined by a maximum entropy ensemble condition, which is another way of saying that we are looking at quadratic actions, Gaussian ensembles. And for them, there exist a handful of methods to compute these correlation functions now within the matrix theory as a function of S. And a few, just two examples are shown here just for illustration. In doing this, we distinguish between matrices of different antilinear symmetries. And we have to distinguish between 10 different cases, 10 different symmetry classes, and two of which, for two of these, I've shown the correlation functions here. The first is a matrix theory for just Hermitian matrices, no more structural information, which we call class A in our language, or it's also known as a unitary ensemble. And another one is class A2. These are matrix operators which are time reversal invariant in a way where time reversal squares to -1. So two different correlation functions universally expressed as a function of S. You see the plots down here, and they illustrate 2 points which will be essential for me. First, for large S, that means energy difference is large compared to the average spacing, we can approach these functions perturbatively. At least we can try to compute their envelope functions perturbatively in a 1/S expansion. Now, for small s becoming smaller than 1, these 1/S contributions individually diverge, but these divergences are cut. I mean, there is the actual function is quite regular. Actually, it has to approach -1 in this way in which I define it. So there is a non-perturbative structure going on regularizing our large S perturbation theories. So that's that. And in the recent holographic literature, it has become popular to describe these functions in a Fourier transformed representation, where we consider the S Fourier transform to obtain a function which now naturally depends on a time-like parameter, and this is called the spectral form factor. Again, we can do this separately, symmetry class by symmetry class, and the two functions showed previously are now shown here in the Fourier transformed language to illustrate a few things. First of all, in class A, just Hermitian, we see a structure which has become now very popular under the name ramp plateau. I mean, this was the terminology introduced, I understand, by the West Coast group, Stanford group, ramp plateau. For the symplectic case, you see that the form factor is distinctly more complicated. It has a singularity at tau equals 1 corresponding to S equals 1. And I really want to highlight here, that's my own subjective point of view from chaos, that this ramp plateau business is actually, it's more obscuring than it helps. The point being that for a given chaotic system, no matter which one, obtaining this kind of linear contribution to the form factor is usually, I mean, quite straightforward. Getting the full functional behavior, like in class A2, is distinctly more complicated, and this is not just a formality. There is a lot of physics sitting there. I mean, the actual physics of the short time expansion of quantum chaotic systems is much more complicated than linear. There's only one symmetry class which has this shows this linearity due to a quite subtle cancellation, which is related to a semi-classical exactness principle. For example, Berry identified for periodic orbit systems this linear ramp in 1981, and it took 27 more years to actually get the full series for the form factor. So one usually, I mean, one should be ambitious to understand the full series and not just stop at the linear order. And looking at the recent literature, I think this is a kind of a non-empty remark, right? And I'll come back to that later. Okay, so that's that. Now, let's try to ask, how do we actually make this concrete? I mean, how can we compute these functions, both for realistic models and for random matrix ensembles? The point now is that, by the way, I hear myself talking. I mean, let me repeat, if anything is unclear at any point, yeah, I have a lot of time, or we have a lot of time, please interrupt. Any questions up to this point, perhaps? Nothing, I hear nothing. Okay, I continue. So the point is, I mean, approaching, yeah? So,
sorry, I'll ask something.
Absolutely,
so
sure.
I just wanted to clarify a point. You are saying that irrespective of all symmetry classes to leading order, everyone shows a linear ramp at beginning in all symmetry classes?
Yes, the leading order, if you think of this as a series in 1 over S, which is equivalent to the series, thank you for the question, which is equivalent to a series in powers of tau. Yeah. So just the linear order is always there. It's a linear in tau. Yeah. But then, I mean, for symmetry classes different from class A or different from the unitary class, we get higher orders, tau squared, tau cubed, and so on. And describing them is a more ambitious exercise. That was my statement.
Okay. Thank you.
And in class A, there is a miraculous cancellation of all higher orders, an exact cancellation which connects to the semi-classical exactness principle, which yeah, I'll comment later.
Thanks.
Okay, thanks, Marta. So the thing that makes this correlation function enterprise somewhat different from the topological expansion we had earlier is that we have now two expansion parameters to play with. One is n. Large n is always important. It simply means that we have many levels in the spectral range we are interested in, high dimensional matrices. But now we also have S. And S again is energies differences we are interested in, measured in units of the level spacing. The level spacing is proportional to 1 over n. So we have an independent expansion parameter for fixed n. We can tune S to arbitrary values. Yeah, so two parameters to play with. And this is basically now the chaos correlation function perspective. And the question is now, or the next question I would like to address, how are these two views, the topological one and the one I just outlined, how are they related? And the starting point to this discussion is that if you fix omega, the energy difference, the 1 over S expansion for fixed omega is actually a 1 over N expansion. So it is a topological expansion, and that's a perspective which in our field is usually not appreciated or not, yeah, it's just not discussed, but it's a fact of life. And that means now that we essentially want to do the following. Suppose we want to describe the form factor at a given order in 1 over S. We are then working at a given order in 1 over N, which means that we are operating within a topological sector. Yeah. But now we also want to obtain something which is singular, namely, I mean, inverse power of the energy difference we are interested in. And that means that we necessarily have to do infinite order perturbation theory in H, in our matrix power. So within a topological sector, we do infinite order perturbation theory. Another way of saying it means that in the expansion of the resolvents in powers of H, we need to work in such a way that for each additional power in H squared, we need to have one full index summation such as to keep the 1 over N order constant as we progress in the order in perturbation theory. So this may sound a bit formal. I make this now concrete. How do we do this? This type of perturbation theory is usually formulated diagrammatically, but in our field, in a language which does not use a Toph double line notation, but is somewhat more economical for us, single line notation. And I mean, you get used to it in an instance. Here are two diagrams in the perturbation series formulated in double line on the left and in our language on the right. So you see they are pretty much structurally equivalent at different genus orders. It's just that the single line notation is a bit more ecologically friendly. You have to draw a little less, yeah, less paint needed. And let me show you now on a few examples how these 1 over S orders are distilled from the matrix ensemble. So this first example is the single resolvent where there are no S singularities to expect it, but we want to work at leading order in 1 over N. So that means that we consider the resolvent expanded in a planar order, just planar diagrams. And throughout, I will now, this resummed series, you can resum all these diagrams. I will denote these propagators again by a single line just to keep the notation slim. The first interesting contribution is the two-point function, the two resolvents at planar order. So if you consider this function, and I'm certain you know this, and you want to work at fixed at planar order, but get something singular in 1 over S, you need to sum a ladder. So we sum ladder diagrams as indicated here. And the summation over a ladder, this is just an infinite order summation in this ladder structure, gives you a 1 over S singularity. So,
sorry.
Yeah.
Question. I mean, you're restricting to cubic potentials here?
No, this is for the moment, this is a Gaussian ensemble.
A Gaussian here.
Yeah, this is a Gaussian. I comment on the cubics and later on. Yeah. Thank you. But this for the moment is Gaussian. We are working, I mean, why is it Gaussian? We want to do maximum entropy. That's the one, I mean, this is quadratic, which we need in chaos. Good. So we sum the series 1 over S. And we have now 2 of these ladders. So this gives us 1 over S squared and Fourier transforms to tau. This is the ramp. Now comes the next topological sector. This is next order in 1 over N, next order in S. So this is one of the diagrams here contributing. There is a handful more, not many. So the experts here will see or immediately recognize that you can draw this beast here on a torus without intersection. It's a toroidal diagram. And notice the structure. We have a bunch of ladders. We also have here these kind of intersection points, which are called Hikami boxes in the language of our field. And each Hikami box is in turn obtained as a sum of ladders. So it's a somewhat non-trivial object. And it contributes the power of S. And if you do then the counting, you see that you are at S cubed order here, which corresponds to tau squared. In the unitary case, in class A, this beast and a few of its colleagues cancel out, but not in general. So this is how this perturbative expansion, double expansion in 1 over N and S is organized. Before we leave this, one more remark. I guess it should be obvious to people here, but let me still point it out. At each order 1 over N, we obtain many diagrams. I mean, of this given topological order. For example, this one here shown on the right, but only very few which have this regular ladder structure are also singular in 1 over S. So the metaphorical way to think about it is that we have for each order 1 over N or each genus, we have a huge set of diagrams, and within them a preciously small singular set, which we are interested in primarily here in this chaos application. Yeah. So that's kind of the connection on the perturbative level between topology and this correlation view. Now, next and the final point where perturbation theory is concerned, if you look at these diagrams, their structure, at some point you grow tired of always drawing this color, this fancy letters here, and you abbreviate them. So we can introduce a shorthand notation, a propagator, a 1 over S propagator, and we have vertices, these Hikami box or Hikami hexagon, Hikami octagon, and so on, which all contribute in order S. And they, in a way, define vertices. And in this language, the perturbative expansion of the two-point function or the form factor assume the form as indicated here. And you begin wondering or speculating that this could be the perturbative expansion of an effective quantum field theory. I mean, it looks like a quantum field theory. And I want to argue that just from the structure of these diagrams, we can almost uniquely fix or determine what kind of quantum field theory this must be. We just have to notice some salient features of this expansion. First of all, its propagators are singular in S, or in a way they are massive in S, such that for zero mass they diverge, but they are otherwise structureless. I mean, there is no dispersion here, meaning that we are dealing with a zero-dimensional field theory. I mean, no wonder, these are ergodic quantum systems, there is no dimensionality here. Our field theory cannot have a fixed vertex degree, it cannot be a phi to the 4 theory or whatever, because we have vertices of arbitrarily high order, I mean, hexagons and octagons and so on. And we also know that the perturbative expansion is an asymptotic one. I mean, it's singular for large, it's regular for large S, but each diagram individually diverges for a small s, yet we know that these singularities must be cut. And this must be non-perturbative mechanism. And I want to reason that if you now check your literature knowledge, these are features almost uniquely specifying our quantum field theory as a nonlinear Syk model. There must be a nonlinear Syk model sitting there, and a nonlinear Syk model that does the following, that represents some kind of spontaneous symmetry breaking mechanism where S, our mass parameter, is an explicit symmetry breaking parameter in such a way that if I tune S to 0, the broken symmetry gets restored. So it's like a spontaneous.
Sorry, can I ask a question? Can you hear
Yes,
me?
of course.
So my question is, in how many space-time dimensions is this QFT? I mean, you have
0.
a
0 plus 0, Johanna, 0.
But what's the difference to the matrix model you were considering beforehand? I mean, why is it a QFT?
They also didn't have a dimension. I mean, you think intuitively, think of some kind of collective quantum system, nucleus or whatever. You wait a long time, it becomes ergodic, it becomes totally structureless. There is no structure left, no dimensionals, nothing. I mean, no dimension. It's zero-dimensional system.
Can I make a comment, Alex?
Yeah.
You can think of this as a higher dimensional quantum field theory, but what Alex is discussing, because that's the important part, is just the zero mode in this case.
Okay, but sorry, I have a very basic question. I don't understand. I mean, you start with a matrix model, but in 0 plus 1 dimension, this is already a quantum field theory if you want. So what is different?
Yeah, right, Johanna, you're absolutely right. What I suppose you want to consider now, not a you want to consider a higher dimensional matrix model, yeah?
Yeah.
Okay, that's fine. In that case, I would obtain the higher dimensional nonlinear Syk model here.
Yeah, but the
And for
difference
the-
is you're
for
not
the time-
integrating over an affine space, you're integrating over some curved manifold. The thing you're integrating is a curved manifold, like in a nonlinear Syk.
Okay, good. So it's a different, well, you're just merging to a different model. I mean,
No, but they do have a precise correspondence, which is basically after what Alex called the Taoist time. Even the higher dimensional case reduces to the zero-dimensional one.
yeah.
Some of them, yeah.
This is in some sense the context of this lecture, which Alex showed in the beginning. So an arbitrary quantum system, even one with higher dimension, after the Taoist time, it will reduce to the sigma model for the zero-dimensional case.
Yeah, if your matrix model to begin with was put in a box. If it is not put in a box, if it's you have a matrix field theory in the entire universe, I mean, really in expanded space, I'm not claiming that it becomes ergodic. I mean, we have to, but this is about ergodic quantum systems that become ergodic. And what Julian is pointing out that even if you start with a higher dimensional matrix model and you put it in a finite box, it will become ergodic at long time scales. And then it's described by a equivalently zero-dimensional field theory or the mean field, homogeneous mean field of a quantum field theory.
So I'm just asking about your strategy. I mean, why do you construct this QFT? Because you want to describe the zero modes, or
no? In general system, I mean, in a more, I'm starting here from the zero mode sector. Yeah, in more general systems, and I give you two examples later on. I mean, there will be two examples upcoming which illustrates this point. One is Young-Mills and QCD, and the other one is the SYK. This here is a zero mode sector, and on top of that, and on top of that, you have then spatially inhomogeneous fluctuations in what actually becomes a non-trivial spatially extended effective field theory of nonlinear Syk model type.
Okay.
But Johanna, I mean, it's a very good question. I think it will become clearer as we develop and go on. I mean, in the end, I will give you this higher dimensional perspective.
But in some sense, maybe the last thing one can say is that indeed the structure that Alex is describing is more powerful than just the zero-dimensional matrix model, but there is some correspondences between them and certain limits.
Yeah, right. I'm getting there. Slowly approaching it. This is in a way a bottom-up approach, if you. But anyway, let's go on a little, and I hope it will become clearer. So for the time being, I just want to argue that this kind of hierarchical double expansion, 1 over S and 1 over N, is effectively described by a zero-dimensional quantum field theory. And it will be of nonlinear Syk model type. And our goal is now to kind of identify this in precise terms. And in this way, to develop this geometric perspective. By geometry, I mean the field manifold of this nonlinear Syk model. Yeah, that will be a non-trivial one. And in order to do that, we need to change gears. I mean, at this point, this topological expansion business is really maxed out its capacity. We need another approach to identify this effective quantum field theory. And that is more algebraic in the following sense. We consider a ratio of spectral determinants. I mean, this must be a very familiar object in this field, averaged over our matrix ensemble. And from it, we can then obtain our correlation functions by differentiating these energy arguments to compute resolvents. Now, this ratio of determinants affords a natural representation as a Gaussian integral, where we need both. We need commuting and anti-commuting variables to generate determinants and inverse determinants, respectively. Yeah. So we introduce, in this case, 4 determinants. We introduce a 4-component integration variable, and all this is then averaged over H. And our integration variables now naturally live in a tensor product space, which is the product of 2 spaces. One is a 4-dimensional graded space, simply containing 2 bosons and 2 fermions, and I call this the flavor space. And it's tensored with the color space, which is simply where our Hamiltonian lives. Yeah. So we have an integral, Gaussian integral over variables which carry a very high-dimensional representation under a graded group U capital N times small n. Small n is 2 here in this case, in the simplest case, slash capital N times small n. Okay, so far so good. And now it comes. This is now technically the main point, Johanna, and this is why I think this effective approach is useful. There is a beautiful duality. There's a duality, and it's exact, and it applies to generic polynomials here in H. Duality between our original functional integral and another one. And this second functional looks structurally perfectly equivalent to the first one, except that here in the dual one, we integrate over matrices in flavor space. So 4-dimensional or n/n dimensional graded matrices in this low-dimensional flavor space. And this integration here replaces the integral over H in the upper one. And the statement is that these 2 functionals are equivalent, they are identical. Now this duality extends to symmetries. Our original representation, at least in the limit where all energy arguments are tuned to identical values, I mean in the explicitly symmetry unbroken case, is invariant under the flavor group, under UN/n. I mean all these psi's are equivalent in this case. So we have a flavor symmetry, a low-dimensional flavor symmetry. In the representation on the bottom, we are no longer flavor symmetric, but now we are color symmetric, simply meaning that we have integrated over all H's, so we have projected onto the singlet representation in color space. So we have this nice duality, and it goes back to the late 70s and was then further developed, and that's just what it is. Now we can ask, what is this representation good for? I mean, except for its aesthetic value, perhaps. Its merit becomes obvious once we integrate over psi. I mean, psi is a Gaussian integration variable, we can integrate it out. And we now see that this dual representation presents us with a win-win situation. First of all, we have a lower dimensional matrix integral. I mean, we like to do simple integrals. I mean, 4-dimensional matrix integral is simpler than an n-dimensional one. And second, we have a large factor n sitting up front, the color, dimension of color space. So that means that this integral now, which is an exact representation, can be processed in a stationary phase program. We can do stationary phase stabilized by large n. And let me quickly outline the cornerstones of this program. So if you ask what are the stationary points of this action up front, you realize that they have finite imaginary parts, and these imaginary parts are proportional to the imaginary parts of our energy arguments, which are infinitesimal. I mean, we are looking at correlation functions at E plus minus I delta. This is what we call causal symmetry breaking. And it's conceptually the same thing that you have when you cross a spectral curve in other approaches to matrix theory. So it's just kind of a causal non-analyticity. So you have a mean field which spontaneously breaks this kind of plus minus I delta infinitesimal symmetry. Yeah. Question?
I don't think there was. Just keep going. Thank you.
Okay, I continue. Thanks. So if we now look at this in a situation where our energy argument, these sets, are chosen so as to be relevant for the computation of a two-point function, means E plus minus omega halves plus minus I0, the mean field reflects this kind of structure. And this is another way of saying that the symmetry is now broken down from U2/2 to U1/1 cross U1/1, which means we still have full supersymmetry in the game between bosons and fermions, but the advanced retarded symmetry plus minus I delta is broken. And since this is spontaneous breaking, there is a Goldstone mode manifold which governs this functional integral. And this Goldstone mode manifold is simply the full symmetry group U2/2 divided by the unbroken group, as always. And this is what we call the supersymmetric space A3 rank 2/2 in a certain language. But intuitively, and I mean, you're experts here in this community, intuitively you can see it, this is just the product of a sphere in the compact sector and in hyperboloid in the non-compact one. So this is our Goldstone mode manifold. This is the geometry of the problem in class A. It is this product manifold, and they are connected by Grassmann generators. So that's our integration manifold. And the statement now is that if we do this Goldstone mode integral, we get our correlation functions. So to make this precise, one considers now a finite symmetry breaking omega expands to first order in the Goldstone mode. The Goldstone modes are here represented in a standard representation, just symmetry acting on the symmetry broken mean field. And the action is, no surprise, is linear in our symmetry breaking parameter omega divided by level spacing. And if you integrate now, do this four-dimensional integral, you get the exact RMT correlation functions. So we have a very user-friendly representation of the exact RMT correlation functions. Let me emphasize a little more this geometric perspective here. So here's what we want to get, the spectral form factor in a time representation. So if we look at short times meet large energies, large S, we have a significant symmetry breaking in our integral. And that means that we can perturbatively expand around the mean field origin, the bottom of our integration manifold. And if we look at this perturbation expansion in 1 over S within the framework of this flavor integral, we recover the diagrammatic expansion, no wonder. So this is the diagrammatic expansion which we wanted to reverse engineer in the beginning. If we now push things and go to larger tau, means smaller s, we notice, oh, our functional integral has a second saddle point, because you know it's a product of a sphere and a hyperboloid. So the south pole of the sphere is another high symmetry point. It's a stationary point of the functional integral called the Altschuler-Andreev saddle point. And technically, this is an unstable vacuum. So if you do perturbation theory here, you again obtain diagrams. They are in a nominally divergent series, but you can do some big rotation. And if you do that, you get a better approximation to the correlation functions. But eventually, if we go to really small s or large tau, we are restoring the symmetry. I mean, the explicit symmetry breaking now goes to 0. We are in low dimensions. We are in 0 dimensions. So in 0 dimensions, there is no spontaneous symmetry breaking. We need to integrate over the full manifold, the full sphere and the hyperboloid up to 1 over S orders. And that then gives you the exact correlation functions in all symmetry classes. I mean, these integrals I'm discussing exist for all 10 classes. They are exactly doable in all cases. And you get the RMT correlation functions from this framework. Good. And the geometry of this, let me finish this sentence. I mean, the geometry of this symmetric space, that is, for me, I mean, in my experience, this is a gold standard in the analysis of chaotic systems. once you have this geometric structure under control, you know your correlation functions. And this is what I meant by a geometric approach. And the topological expansion is the low S large S asymptotics to it. Yeah, question.
Yeah, I have a very naive question.
Sure.
So in geometry, right, we have a two sphere and the hyperboloid attached to one pole.
Yes.
But normally I would imagine, is there another hyperboloid attached to the other pole?
No,
Or-
no, it's just one hyperbolic. It's my stupid drawing here. You have one hyperbolic. I mean, you have sort of the non-compact partner of a sphere, one copy of it, and a sphere. It's not two hyperboloids and a sphere. I mean, it's just one. I mean, I think of naively, I think of the hyperboloid as simply a non-compact version of the sphere, considered as a symmetric space.
No, but isn't Anton right? I mean, in some sense, you could. I mean, it's not a different hyperboloid, but the thing always has a product structure, sphere times hyperboloid, and this is true of one of the poles, but also true about the other pole. I think, was that your question, Alex?
Yeah. Yeah.
Okay, then I formulated.
I think you're right. Yeah.
Yeah.
Product.
Yeah,
Product
it's a product manifold, and that's of course true at both points.
Okay. Okay. Thank you.
Sure. Yeah. Thanks. So that's it. Now, this is what this kind of zero-dimensional flavor integral approach to chaotic systems. And now, let me, in the third part of the talk, try to put this into a context. And now I'm pushing a little bit my limits. Let me give you two examples where this way of thinking is kind of plays a certain role. The first example is simply a toy example meant to illustrate that this color flavor duality should be familiar to all of you. And that's actually where the language color flavor came from. And this is a large NQCD. Large NQCD is an example of what we just discussed, a slightly different reading. So consider a Hamiltonian and think of it as an Euclidean Dirac describing n copies of quarks, I mean n flavored quarks, and they're coupled to a color gauge field, SUN color gauge field, which assumes the role of our randomness now. In this case, we are dealing with a Hamilton operator which anticommutes with gamma 5. And in our language, this means that this is a matrix ensemble in class A3. So A3 is this kind of chiral symmetry. And now the role of the color symmetry is the left and right, flavor symmetry is the left and right flavor symmetry to SUNs. QCD flavor symmetry. The symmetry breaking omega is now introduced by the quark mass spectrum. In this case, it's not natural to talk about graded flavor space. I mean, we have fermionic quarks, so there is not a supersymmetry aspect, but that's a detail now for me. The role of the mean field we were discussing, it's a chiral condensate around which we have now a Goldstone mode. And these Goldstone modes, flavor Goldstone modes, they are the mesons. I mean, the meson fields, and they populate now a Goldstone mode manifold, which in this language here is symmetric space A rank n. The sigma model now, and this is now Johanna for you, this is now naturally defined. It's not a zero-dimensional one, it's defined in 4D Euclidean spacetime. So we have a sigma model in 4D Euclidean spacetime, and the sigma model is the Weinberg-Lagrangian, which I know it is a Weinberg-Lagrangian, maybe it goes by different names. The Meson-Lagrangian, low energy QCD. And the diagrams we were discussing, this kind of diagrammatic expansion, which now is formulated in 4D, is QCD chiral perturbation theory.
Sorry, can I just ask one quick question? So normally there's an axial anomaly in QCD, but I guess you're just not considering that.
Oh no, we have all this in our sigma model business as well. So for example, when you consider topological insulator, yeah, this is a higher dimensional disordered chaotic system, and a topological insulator in class A3 has a chiral anomaly. You then obtain a sigma model, flavor sigma model, which reflects this anomaly. But if you go to the zero-dimensional limit, if you put it in a box, go to the mean field limit, then you obtain these single low-dimensional integrals we were discussing.
Okay.
Yeah.
Thanks. Yeah.
And actually, I mean, this is a social remark in Quant Mat, especially in the analysis of topological disordered quantum matter, we have been going shoplifting in QCD and particle physics. I mean, we have been importing all these concepts to our field. No? Good. So that was one example. Now, let me consider another example, which is closer, hopefully, to the motives of this meeting. This is now SYK physics. I want to look at the SYK model now. I guess SYK model everybody knows, right? Yeah. I mean, it's down here. I mean, it's a large number of Majorana fermions subject to a random all-to-all interaction proposed by Kitaev as a candidate for a 2D holographic principle. And I want to look at it now. I forget about this, and I want to look at it just as a chaotic system. For me, this is now a chaotic system. Chaotic, why? Because these J's are random. It's not a random matrix. It's not a matrix theory now, but it is a chaotic system. And let me kind of stress that for a generic chaotic system, we have different avenues for approaching it. Theoretically, we can do numerics. We can try to do a semi-classical expansion like the one we discussed previously for matrix models. We can also try to identify our causal symmetry breaking mechanism, and from it distill a flavor matrix integral. And once we have that, we can hope to describe variables, observables non-perturbatively. Yeah. So this is what we can have, and let's now see how SYK physics fares in this context. First of all, there is numerics. For SYK, we can do numerics, and it has been done. There's classic work showing that the SYK model fulfills the Bohigas-Giannoni-Schmidt conjecture, although it doesn't have a canonical classical limit, but it is faithful to RMT at large timescales and small energy scales. This is shown here from some numerical data. But I also want to emphasize that for large energies beyond our so-called Thouless energy, there are deviations from RMT. So you see here in numerics, there are deviations from the RMT number variance curves shown here. And in the form factor, you see this famous, what is it called, dip ramp plateau structure. If you look close enough, you actually see subtle differences, including at large times. So I come back to that. Here, one of these curves has this little cusp in it. And this cusp is actually typical for a symplectic form factor, but it should be a full divergence in RMT. In SYK, it's just a little cusp. And this is not an accident. This is actually real physics. I show that in a sec, but let me just for the moment take note that we have a powerful numerical approach to this system. Now, we also have causal symmetry breaking and an effective field theory. So for this system, one can derive a flavor integral, which we discussed before for random matrix systems. Here we derive this functional by different techniques, an integral over flavor matrices for the SYK system. Now this is in the Johanna sense, this is now a non-zero dimensional theory. Our fields now, it's just indicated here, carry indices in Fock space. So they have a dual structure in Fock space and in flavor space. It's a somewhat more complicated animal, but we can analyze it by the methods of the field, of our field, and really obtain quite powerful descriptions of SYK physics. Let me illustrate this here on the example of the form factor in the non-perturbative regime. So I mentioned these little cusps here. Look at this one, and in RMT there should be a singularity. The SYK model actually rounds the singularity by non-ergodic, non-RMT corrections, many-body corrections. And this is here shown, this is data from Jacques Weberschott for 56 Majorana fermions. So red would be RMT, blue, the zigzag curve is the actual SYK model, and the solid blue or smooth blue is what we get from the non-zero dimensional effective field theory, which only for n to infinity then reduces to the ergodic factor where we get RMT. So what I want to say is, where SYK is concerned, we do have this flavor matrix integral approach. We can describe observables from it. What we do not have is a nice semi-classical expansion. The point being that the SYK model is formulated in this crazy Fock space, exponentially high dimensional Fock space, and I just don't know how to draw meaningful diagrams there. But this is not a disaster. We have our functional integral, which is which gives us even more information. So that's that. Now I'm mentioning this here in order to draw a connection to now holography. Yeah? I mean, what can we learn, if anything, from this particular viewpoint, this flavor integral viewpoint about holographic correspondence? And that makes one look at the proposed approximate holographic, I don't know how to call it, holographic dual or holographic partner of the SYK model, which is JT gravity. And what can we say about JT gravity? So for JT gravity, we can't do numerics, at least I'm not aware of any. I mean, it's gravitational fast integral, no natural numerics. But what we do have is the most beautiful semi-classical expansion. So we have a diagrammatic expansion, and that is the way I understand it, the story of Schenker, Stanford, and Saad, 2019, which let me briefly recapitulate what they did, at least in my understanding. They look at the JT partition sum, now organized as a topological expansion, genus expansion of the structure that seems to be canonical in the field. So we have a topological action, we have a moduli space integral, we have, in the presence of boundaries, which we need to compute correlation functions, we have boundary wiggles, and all this is weighted by the Schwarzian action. So now, Schenker, Stanford, and Saad tell us to do the following. Consider a matrix model fine-tuned to have a spectral density in the double scaling limit, I mean, close to the boundary, which matches that of SYK, the proposed boundary partner. And once we have this matrix model, we can apply the topological recursion program mentioned in the beginning. And this we can compare to the topological expansion of the JT partition sum, a la Mirzakhani. And it turns out, and I find this most beautiful result, it turns out that there's quantitative agreement. That's wonderful. So in my understanding, in my mindset, this means that the semi-classical expansions of the matrix model, the diagram expansion, and that of JT coincide. And since the full topological expansion of the matrix model includes as a small subset the singular contributions, the diagrams we discussed earlier, the same must be true on the gravity side, and one can check that this is indeed the case. So perturbatively, this correspondence seems to be to all orders under control, which is wonderful. So we have the semi-classical expansion. Now, what we do not have is the causal symmetry breaking principle. At least I haven't seen it, and I personally think it's just not there. There is not this mechanism of the breaking of a causal symmetry, and hence no non-perturbative description of observables. So the correspondence is perturbative in nature. That's my own belief. I mean, I'm happy to be proven wrong. This is what I personally believe. And the reason is that the JT partition sum is by design a sum. It's a series over topological sectors. And we need to know that the completion of the program, the full correlation functions, are non-perturbative. So somehow one needs something more. I mean, that's at least my own prejudice. And now this is now really pushing my limits, and I'm above my pay grade. Let me just mention a few things which all of you here know much better than me. There are other theories in the portfolio of 2D gravity. Just to do the name dropping, there's minimal string theory, which is related to a matrix model, the Kontsevich model. And there are concepts of string field theory. And one thing Julian explained to me is that in minimal string theory, you actually have the causal symmetry breaking principle. It's there. There is a duality between probe branes and color branes, and one can really identify this symmetry, this duality principle I stressed in the beginning. So it looks like minimal string theory tends to do the job. What I personally do not well understand, and I would love to learn, is how this is now connected constructively to the perturbative expansion in JT gravity. So this kind of semi-classical correspondence I personally don't understand. So for me, there are still question marks left. But I think I'm anyway, I'm above, out of my comfort zone here. Let me just wrap up. I think the following. From my own experience in the field, all chaotic quantum systems, really no exceptions, show this causal symmetry breaking mechanism. It's super robust. There is a subclass of ergodic systems, which I have been focusing here in this talk. I mean, one matrix models, for example, in which the symmetry is broken and then restored at large timescales. Not all chaotic systems do this, but ergodic systems do. And if this is the case, the physics at large timescales is in one-to-one relation to a geometry of a single copy of this flavor manifold. Which one depends on the symmetry you're looking. And maybe the search for this geometric principle can be useful in a holographic context. I mean, that one goes fishing for this symmetry breaking principles and these geometric structures. And yeah, that's the only thing I wanted to maybe propose. Yeah, thank you for your attention. Thanks.
Thanks a lot, Alex, for the very beautiful